So in this video, we're going to be looking at the engineering design process. And the engineering design process is a process that you can use to help you think about the problem that you have, define that problem, and then ultimately develop a solution. Here's a process that we're going to be using. It comes from an engineering curriculum called Project Lead the Way. You'll see it out if you search for engineering design processes out on the internet. This one has 6 steps. That's what I like about it. Some of them, ITEA's engineering design process, is 12 steps, and I just want to try to keep it simple. Basically, first we define the problem, then we generate concepts, develop a solution, construct and test a prototype, evaluate a solution, and then present a solution. The engineering design process is designed to help you. It's to serve you, not you serve it. It should be something that you use to help you think about each different part of the problem, really be able to summarize the problem, think about your criteria and your constraints, and then ultimately develop a good solution that you can test and then present, and then ultimately hopefully manufacture, sell, give people access to, and then innovate upon. So the very first step is to define the problem. First, we need to identify the problem. Is it actually a problem? Are there already solutions out there to this problem? Something that is off the shelf that we can get and use to make our lives easier and be able to solve this problem. Is the problem worth the effort it will take to solve it? Is there already something out there that we can do that will be a workaround? Is there a close enough solution that we can use so that it's not even worth how much time it would take for us to try to develop a custom solution? We need to list out the design constraints and the criteria. The criteria being the things that we know we have to do. The constraints being the limitations, the things that are going to limit us. So as an example, criteria might be if I'm designing a product, it needs to be able to work for both people who are right-handed and left-handed. So that might be a design criteria. We have to consider that whenever we're designing it. A constraint might be that we need to have a solution in the next 3 weeks, or we need to be able to manufacture it and have it in the market in the next 3 months. One of the big one of the big constraints is going to be budget. Different types of manufacturing techniques require a lot more money than others. 3D printing makes each part expensive, but manufacturing it is cheap, relatively speaking, for just 1 or 2 of those products or small batches, depending on what material you're manufacturing it out of. If you want to go injection molding for plastic parts or die casting for metal parts, then it requires a lot more money to initially set it up, but your average part cost in the end is much cheaper because you can manufacture them in bulk and really bring the costs down. So you need to think about what the costs are to get to market and to develop the solution, and those might be some of your constraints. Then you need to develop a design brief, and a design brief is basically just a detailed description of the problem now that you've fully thought through it, and the criteria and the constraints. And this again is to help you be able to summarize and clearly communicate the problem, because you need to understand the problem fully if you're really going to be able to develop some solutions. Then we move on, we're going to generate concepts. Typically you're going to want to start by researching, are there existing solutions or similar problems that have existing solutions, and how can those solutions transfer over to our exact problem that we've defined in our design brief. We also want to go through a process of brainstorming. And for brainstorming, we're thinking about quantity, not quality. So brainstorming, you do not evaluate, oh, that's a good idea or that's a bad idea. You're just throwing out and documenting ideas to try to come up with potential solutions to the problem. You want to reconsider the design brief. As you've started to try to generate concepts, is there anything that you have come up with that will change the constraints or the criteria? potentially adding constraints. So if you start to think through concepts and you realize that you're going to be limited to a particular type of manufacturing process, that particular manufacturing process might add additional constraints to your problem, and you'll have to design around that when you're developing a solution. This is why engineers really need to understand manufacturing and how things are built, so that whenever they're designing solutions to problems, these clever designs, they can understand how to design it in such a way it can actually be manufactured. You're going to select an approach to the problem. This doesn't necessarily mean a solution, but maybe a broader approach. Like I was mentioning before, if you're going to be doing small batches of products, potentially 3D printing could work. And if that's the case, then there are certain things you can and cannot do with 3D printing, and you need to consider that when you're developing your solution. You're going to potentially use a design matrix, and a design matrix is very simple. So if you have idea number 1, in the first row, first column might be a particular criteria or constraint, and you're going to score each of those criteria and constraints, maybe 0 to 5 or 1 to 5, 1 to 10, and then you can sum up all of those columns to figure out which one is going to have the highest score, and that could potentially be your best solution. It's just a tool to try to help you narrow in on a potential solution to the problem, the best potential solution to the problem. And then you need to evaluate, is the needed technology, does it exist for the best solution? If it doesn't, then you can see here on the chart, you may need to go through a process of scientific research in order to try to develop the technology. And we're going to talk about at the end an example of a company who did that and is doing that, and why it was worth the effort to basically hit pause on trying to solve the problem, develop the technology, and then come back to it later. Then you're going to develop a solution, and this is when you take that decision matrix and you've come up with your best idea. Now you actually need to plan out the exact details of that best idea, that solution. This is going to include technical drawings so that you can build this prototype. Those technical drawings are going to have exact dimensions on it. They're going to define the materials that it's going to be made out of. Better yet, you can design it in CAD. If you design it in computer-aided CAD, which stands for computer-aided design, you can use programs like SolidWorks, AutoCAD, Fusion 360, Onshape. Onshape is one that we'll be using. And what that does is it allows you to assign materials. You can see the exact volume of the design. You can see what the mass will be of the design. This will help you to estimate what the costs might be depending on how you're going to manufacture it. Additionally, you can see how parts are going to interfere with each other if they're going to be moving. If those individual parts are going to interfere with each other and it won't be able to function the way that you had envisioned. CAD is incredibly helpful at seeing those things before you even go through the process of building a prototype. And then we need to verify that the developed design actually solves the defined problem. Did we get off track? Does this still meet the design brief? Then we want to construct and test a prototype. We want to build a prototype and plan out how to test its performance, its usability, its durability. We may need to develop or design test rigs and fixtures that we can use to test those things for the prototype. We want to collect data along the way, and we want to analyze that test data. This is part of this process that we're going through to really be able to evaluate the effectiveness of our solution, our design, evaluate whether it actually best solves the problem. And we want to generate a test report that takes that data and potentially and puts it in the test results so we can see how it did. But we also want to potentially update the technical drawings or the CAD if we had to make changes. Again, once you start building something, you might discover, hey, the way that I designed this, it's impossible to build it this way because of tooling and such, manufacturing process. So I've got to change this, and if you make any changes, then you need to update your technical drawings for the future. Then we want to evaluate the solution. How effective was it in actually meeting everything in the design brief? Reflect on the design. Are there things that we can improve now that we've actually built a prototype? it's going through this process, you're going to discover and learn all kinds of things. This isn't a one-off. This is a continuous improvement, iterative process. And we also want to revise and optimize the solution to better meet the criteria and the constraints that we've defined and stated in the design brief. Then we've got a good solution. We want to be able to present the solution. We need to present it to the people who decide whether or not we're actually going to spend the money to manufacture this. If you're a part of an engineering team, you need to continue to document the project in the project portfolio, or you might be using an engineering notebook that has other things in it as well to document everything that you've been doing. And then you need to develop a formal presentation that you can use to communicate the problem in full from the design brief and the proposed solution, how you came to that solution, and all of that test data that you collected, analyzed, and put in that test report. This is what enables you to be able to say with confidence that this is the best solution to the problem. We've thought through all of these things. So that's great, but sometimes, you know, the Latin word for engineer means clever design. Sometimes engineers are so clever that they add in complexity where they don't even need to be, there doesn't need to be complexity. And Elon Musk has a quote where he says, "The best part is no part, the best process is no process." And for those of you who are not familiar, Elon Musk owns a significant portion of Tesla, is the CEO of Tesla, SpaceX, the Boring Company. He's an innovator, creative thinker, an engineer, very strong in physics. And his idea is that the best part is no part. If you can eliminate a part, think about all the complexity, the cost, the effort to maintain that you have just eliminated. The best process is no process. Again, if you can get rid of a manufacturing process so that you don't even have to include it, think about all of the machines that were necessary to have that manufacturing process that you just got rid of. Think about all the people who had to maintain those machines that can work on other parts of the problem. Again, simplicity is key. So I'd mentioned earlier about a company who had gone through this process of this design process and had realized that the technology for something did not exist. So when Tesla first started manufacturing vehicles, they manufactured the Roadster. And the Roadster was actually, they used a body from a Lotus, which is another automotive manufacturer, as the body for the Roadster. And they just basically stuffed batteries and a motor in it, electric motor in it, and other things, the software that went along with it, the control systems. But they didn't design the body. Well, eventually they sold Roadsters and got money, and they grew their manufacturing abilities and engineering abilities, and they designed their own structural body. And for designing a vehicle is very challenging because you've got to not only have the strength so that the car doesn't fall apart when you go over bumps, it has to protect the occupants, and there's a lot of safety tests that have to happen. So how cars are designed is really complicated in order to be able to pass all of these safety tests that vehicles have to go through. You can see here on the left, the Model 3 body structure. It has 171 pieces of metal that are highlighted. And basically the way that most vehicles are manufactured is they have these stamping machines. They put a piece of flat steel in, a sheet of steel. They stamp it and it cuts and shapes the metal. And they have all of these individual pieces of metal, and then the robotic arms are going to then basically weld all of these individual pieces of metal together into this structure. Well, there's this idea of first principles thinking. First principles thinking is basically thinking like a child, where you ask, well, why? Why is the sky blue? Why is this? As you grow up, sometimes you just assume that because things have always been a particular way, they need to be that way. And first principles thinking is saying, whoa, let's go back to the basics. Is this the best way? Is there a simpler way? Is there another thing that I can do to completely eliminate processes or eliminate parts? And that's what Tesla did. They thought, toy cars, injection molded cars, you basically have this mold and you squirt hot plastic in and it fills the void, and boom, you got your part. That's way simpler than if you made all of these individual plastic parts and then you had to glue them together, melt them together to make this complicated part. So they asked the question, can we use die casting, which is what basically you take melted metal, molten metal, and you high pressure shoot it into these molds that are pressed together really hard, and it fills the void, just like shooting plastic into this mold would work. Use die casting to do it with metal. So they said, could we use die casting to actually create the front and the back of a Model Y, which is their which is their SUV crossover vehicle? And the answer was no. The engineering wouldn't work because they didn't have a way to do parts that large. One, because they didn't have a metal that they could do that with without it. It wouldn't fill all, the metals they had would not fill all the voids. It would cool down too much. So they had material scientists develop a new alloy, a custom alloy that they could use in what they call the GigaPress, which is this huge die casting machine. And they're able to create these entire huge molds, parts that are the front and the rear of these huge castings that are the front and the rear of the Model Y. And this is one of those cases where you think, man, that's complicated. That took a lot of engineering, a lot of science, a lot of work. They had to develop these tools. Was it worth it? And the answer is, in this case, yes, it was. They did the math. They calculated out. If we can do this, we can eliminate so much room in the factory that it takes to stamp all of those individual parts, all the robotic arms that have to weld all those parts together, and what it costs us to develop this solution is worth what it will save us in the future. But they couldn't do that when they were a brand new company. It was too expensive. They did not have the resources to spend. So there's always with engineering these trade-offs of do we have the resources? What are our constraints? What are our criteria? Let's get something to market. Let's sell it. Let's get some money. And then let's improve on the design. If we can develop a solution that is a good solution and that people want, then we can start to have that flywheel effect where we can develop better solutions. So I wanted to show this as an example. We're going to be talking about first principles thinking. We're going to be talking about ways to simplify our solutions, and we will be applying this engineering design process that you've just seen in this video to many projects throughout this course.